Thank you so much, Andrea and Daniela. It's a wonderful opportunity to be speaking, but it's also a bit daunting to be speaking after George Gershon. So, let's see. Yes, so can you see my slides moving and everything? Okay, so maybe.
Yeah.
Okay, all right. Yeah, so my talk, it's, I think, more applied than the previous talk. And it basically has, I have a couple of complaints about the traditional way of modeling. And this talk is about how we can address those things. So let me start with the very basic, let's say, nomenclature. So we have species, which are chemically identical molecular entities. We all know that, and chemical reactions are basically changes in the physical state of those molecules. But it could also be a birth-death type of reaction, which is basically talking about creation or annihilation of a species, or a combination of these things, where molecules of different species are combining and creating new stuff. And when we are talking about reaction networks, it's basically a collection of species and usually a finite number of reactions. It could be infinite, but we'll talk about only the finite number of reactions. Yeah. And then, of course, one example is the Michaelis-Menten enzyme Kinetic. And there's a reason why I'm picking this example. So what happens there is you have 4 different species. So you have an enzyme, you have a substrate, and enzyme substrate, they combine together to form a complex, which is sometimes called the enzyme substrate complex. This combination is not always successful, meaning that it's reversible, so it can also break up, and then you get this reaction back. But if not, then the enzyme substrate complex will eventually produce a product and then free up the enzyme. So which is this. So there are 1, 2, 3 reactions and 4 species. So that's a chemical reaction network at the micro level. But you can also use the same machinery, the same type of language to build a model at the ecological scale, at the macro scale. So think of the epidemic models that I think the SIR type epidemic models are a household name these days because of the pandemic. But the SIR type equations are nothing but a chemical reaction where there are 3 species. So you have susceptible individuals, infected and removed, and there are 2 different reactions. So whenever an infected individual meets a susceptible, then the susceptible person gets infected. So you just, yeah, this is the reaction, the infection reaction, and then infected individuals, they also recover following certain exponential distribution. So those are like very common examples of these things. And the traditional way of modeling is to use the deterministic model, where you use ordinary differential equations or partial differential equations for the concentrations. For the Michaelis-Menten example, if we have mass action kinetics, which is basically inspired from physical chemistry literature, where you assume that every molecule has an equal opportunity to interact with any other molecule. So this gives you this polynomial type reaction rates. So you transform this Michaelis-Menten type of reaction into a set of ordinary differential equations here. Similarly, for the, let's say, SIR model, you get what are known as this Kermit-McKendrick SIR equations. So that's all good. What about the stochastic models, which we might be needing particularly when the species copy numbers are low, or you are at the beginning of the epidemic where there are not many infected individuals. So there is a lot of stochastic fluctuations. And that's also fairly standard. So you use continuous state Markov chains for the counts of these molecules of different species, or these are called species copy numbers. Or if you think of epidemiology, then these are the counts of people in different compartments with different immunological statuses. So number of susceptible people, number of infected people, number of removed people. And then you just write a Markov jump process on the integers, and you can write down the trajectory equations in terms of Poisson processes for these counting counts, basically. And thanks to the random time change representation and the limit theorems proved by Tom Kurtz and others, you can actually show that if you scale those counts appropriately, usually by the population size or the volume or some other scaling parameter that might be appropriate, these stochastic processes actually converge to deterministic equations. So this basically looks something like this. So the idea is, suppose here you have, so on this you have time, and let's say you have a Poisson process which has trajectories like this, which is increasing. And if you do multiple times, you will have like some other curves. And let's say that this is the mean, which is something, let's say lambda t. So lambda is the rate of the Poisson process. Then the Poisson law of large numbers basically tells me that this quantity is approximately equal to lambda t when n is large. So you can use this idea and put it on the chemical reaction network, and then show that, okay, that there is these stochastic and the deterministic worlds, they actually converge. So that's nice. But here is my, let's say, first complaint. The first complaint is that whenever we have a continuous time Markov chain, what we are essentially assuming is that the inter-event times, or let's say the time to the next reaction, those are exponentially distributed, right? And the rates are dependent on just the counts of different types of molecules. And whenever a reaction fires, then everything changes instantaneously. So I think those assumptions are not very realistic, because sometimes there's a significant delay between the start of a reaction and the completion of the reaction. So how do we actually account for these things? So yeah, so the first thing, or first, let's say, consequence of if we agree that, okay, these assumptions are not tenable, then the first consequence is that the CTMC models are actually inadequate. So we need something slightly more abstract or more powerful than the CTMCs. So we are going to do that, but I also want to emphasize that these time delays that I'm talking about, they are actually pretty common and commonly observed in many biological systems. So if you look at gene transcription, RNA protein unfolding, or even in infectious disease epidemiology, I mean, I think it's almost universally accepted that you cannot be infectious right at the moment you get infected. So there's also a time delay. And then in infectious disease epidemiology, the standard approach has been to bring in more compartments. So you say, okay, maybe then SIR is not good, so let's do SEIR. So you put one more compartment, and then say, okay, maybe even that's not good, so we incorporate one more. But we are actually not solving the problem here. We're just maybe reducing the amount of error bit by bit, but maybe there is a different way. On the other hand, this notion of delay could actually be purposefully introduced to account for unobserved, let's say, processes or things like that. So what I mean is that, so suppose I have a reaction that, that's of this form. So from A, I go to some A1, and then to A2, and then there are several steps, and then finally I produce something like B. And then it is quite possible that some of these reactions are actually not observable. So what I can do is I can approximate this whole system by saying that I have a single reaction that is just delayed. So it takes, and then what we put here as the rate, that's a question that we are going to answer. But you can easily take this notion of delay as a tool for model reduction. Now, one way to actually account for this delay is to incorporate what is called, or what I'm going to call age. But age doesn't have to be the actual biological age or the physical age, but I'm going to use the term age as to refer to any sort of covariate that you think might be useful for describing the probability distributions for these delayed reactions. So let me maybe give you an example. So suppose I get this model reduction here. So what I'm saying is, so since the time this reaction starts up until it's completed, I can also represent this equivalently by saying that now this is this. Okay. So what I'm doing is I have a fictitious species F. So I'm saying so this reaction was my delayed reaction, and this is not the delayed one, but instead I'll say that the reaction is age dependent. So I say that whenever this reaction starts, the first reaction starts, I instantaneously create one molecule of this fictitious species F. And then at some point, this F molecule gets converted into B. And this reaction here is age dependent. So it depends on how long ago the molecule was created. And that's why I'm using the terminology age. So I can always do this kind of trick for, even for more complicated reactions, but that's the basic idea. And we can, of course, incorporate other covariates. And sometimes, if you make the model more realistic, then you are probably doing it at a cost, and the cost is usually, let's say, computational complexity. It is true, but we can also use, we will see how we can maybe get rid of or account for those complexities through some multi-scale approximation. But let's see what happens to the scaling of these kind of systems. So this joint work with Haewon Kang, Eben Khuda, and Greg Rampala. Eben and Greg are at Ohio State University, and Haewon Kang is at University of Maryland at Baltimore County. Wonderful collaborators and things like that. So let's take a very simple model that has delay. It's just a birth, death, and a transformation type of reaction. So this is the birth reaction, this is the death reaction, and this is the transformation type of reaction. I'm going to say that this reaction, the transformation, is age dependent as well as the death type of reaction. So these are age dependent reactions, so which means that tau and d, these are no longer constant rates because they are not exponentially distributed anymore. So, but rather these are hazard functions that could describe any arbitrary probability distributions. And I'm saying arbitrary distributions, but it's a fairly large class of distributions. You need to have certain moment conditions, but they're not that restrictive. And for simplicity, I'm just assuming that the birth reaction is Markovian, so that B is constant, but it's not a requirement. And then what do we keep track of? So we need to keep track of more than the counts. So we just, let's say here, keep track of the entire age distribution of the molecules. So these are basically stochastic processes that we keep track of. So what are these? These are finite moments, and these are the Dirac measures. And what are AIs and BIs? So AIs and BIs are the ages of the ith molecule of the species A and B. So I'm placing the atoms at the ages of the molecules, and then I'm summing up for the, over from 1 to the number of molecules here. So these stochastic processes, they're actually keeping track of the entire age distribution of the different species. So these are measured valued processes that are describing the age distribution. How do you, let's say, just to give an example, so if you evaluate these measures against a set, let's say 0.5 to 11.5, this will just give you the count of species molecules whose ages are within this set at time t. So that's how it works. And also when we want to study the large volume limits of these stochastic processes, our intuition somehow tells us that, okay, if we scale it with the volume or something as large as the volume, then they should indeed converge to something deterministic. And that intuition still holds. The maths gets a little bit more complicated than the standard CTMC models, but it does hold. So if we study the large volume limit of these scaled stochastic processes, then we can actually show that they do converge to deterministic measured valued functions. And if those measured valued functions admit densities, then you can actually write partial differential equations for those systems. The proof is fairly standard. It uses standard limit theory for measured valued Markov processes, developed by lots of French mathematicians, as well as Tom Kurtz and many other people. So let me tell you what the limit would be for the example that we considered. So you can show that for this simple birth and death, as well as transformation type of reaction, you get deterministic measured valued functions, and the density basically satisfies a partial differential equation, which is linear here. It has a simple boundary condition and an initial condition. And because the example is so simple, you can actually solve it explicitly here in terms of now this ST, tau and SD are survival functions. This survival function for it. So if you have a random variable, so not many people might know. So this thing is called a survival function. So it's 1 minus the CDF of thing. And if you remember this tau and D, they were the hazard functions corresponding to some probability distributions. So S and tau are the survival functions. So you can actually solve explicitly, and that gives you an equation for the B molecules as well. So that's quite nice that you still see some agreement between the stochastic world and the deterministic world. But as said, this stochastic world that keeps track of the age of each single molecule is, of course, much more expensive to simulate, right? So is there a way we can use the limit theory for these stochastic processes to speed up our simulations? And the answer is actually, of course, yes, but let's maybe also verify whether the limit actually works. So here's a simulation result. So on the left-hand side, so yeah, I'm plotting time here and the shapes of the hazard functions that are chosen. So I have constant birth rate, which is this. And then I have a delayed reaction, which is this. As you can see, it's 0 for a while, and then it's positive, and then it goes down, which means that the reaction, the transformation type of reaction, this is going to be, cannot fire until, let's say, 2.3 or something like that, so at least this point. So this is the minimum amount of delay. And then it has a growing propensity of firing. And then after a point, the propensity actually goes down. And the death reaction is not necessarily delayed, but this is the shape of the hazard function. It's also not exponential. So I think I might have chosen a gamma or inverse gamma for that. On the right-hand side, I have time and then the concentration. So when I have aggregated or averaged out, not averaged out, aggregated out the individual ages. And I have in solid lines the theoretical PDEs, and in the dotted lines, I think I have with these markers, the simulations. As you can see that they actually match up quite well. So and they should, because it's a law of large numbers limit. So that's good to know. But let's talk about how we can use this limit to maybe speed up some simulations. And if I have time, I'll also maybe talk about a couple of other applications. But let's just focus on this simulation aspect. So let's say we have a situation where we know that there are plenty of A molecules available. So intuitively, we know that the PDE approximation should be reasonably accurate for the A molecules at least. But at least in the initial phase, when the number of B molecules is still growing, there will be a tremendous amount of stochastic fluctuation, right? And we might actually be interested in just the B molecules. So what we could do is we can approximate the whole system where by a reduced system and just focus on the B molecules. The initial growth of the B molecules can then be actually just described by a Poisson process, whose intensity is now described by a PDE for the A molecules. So that's the idea behind this hybrid simulation. So essentially what you do is you build a Duke Gillespie type of algorithm where you are still first calculating the time to the next reaction, which is again here exponentially distributed, but the mean is driven by an underlying PDE. So that's what we did here. And here's an example of a simulation, let's say, study. So on X, on the left-hand side, we have the shapes of the hazard functions chosen. As you can see, this is still the delayed reaction. It looks different from the other example. I don't recall what the exact distribution was, but it's, yeah, Weibull or something like that. So these are the different hazard functions that are chosen. And here on the right side, I'm comparing the full stochastic simulations, which are shown in red, and the hybrid simulations, which are shown in green. As you can see, at the level of mean, the hybrid simulations match perfectly the full stochastic simulations, but it actually underestimates the variance a little bit. And the reason for that is that because we are using this law of large number approximation for that already underestimates the variance, you also see this effect on the full trajectory level. So that's the caveat. If you are interested in higher order moments, maybe this is not a good idea. But if you only care about the mean trajectories for P molecule, then this is actually tremendously accurate and also very fast. So just to give you a sense of how efficient this could be. So I'm plotting the ratio of two important metrics for, let's say, computational cost. So ratio of, let's say, the execution time for the full stochastic model and the hybrid model. And for that, you see that the hybrid model is at least 5 times more efficient than the full stochastic model. If you change the metric to memory usage, this is also at least 4 times more efficient than the full stochastic model. And that intuitively makes sense because you are not keeping track of the individual ages anymore. That's one thing. I'll quickly just talk about one more application, and then I'll take questions. That's the simulation aspect, but we can also use this this machinery, which basically links a set of PDEs to a stochastic model to calculate many other quantities. For instance, mean first passage times. So mean first passage times are let's say, very natural questions in many dynamical systems. And these are questions like, how long does it take to deplete all molecules of A, or to produce 10 molecules of B before depleting all molecules of A, and things like that. And because we have a PDE now, we might actually be able to approximate or answer these questions relatively simply, and they will be reasonably accurate. That's the idea. So let's say we are interested in the time required to produce the first molecule of B in this system where we have large number of A molecules already. So then from the PDE approximation, we already know that this can be approximated by just an exponential distribution that has mean that's driven by the PDE solution. So we have an explicit solution for this thing, and the mean of the exponential will be just this. So here's a numerical study that shows how good this approximation is. So again, on the left side, you see the shapes of the distributions or the hazard functions chosen for this particular example. You have exponential, delayed, and all sorts of hazard functions there. And on the right side, what I'm doing is I'm comparing this first passage times from the full stochastic simulations. Those are in yellow here. And then I'm simulating exponentials from this theoretical mean that I just derived from the PDE. And then I'm comparing the density of these things. And of course, they match up, meaning that this exponential approximation to the first passage times is actually quite accurate. So that's good to know, and hopefully useful for some applications. We might also use this to derive some quasi-steady-state approximations for the Michaelis-Menten model. And in the paper, we actually did that. You can also use this approximation for parameter inference using dynamic survival analysis approach. And this is actually quite useful because it allows you to incorporate other covariates. For instance, if you're talking about infectious disease epidemiology, these covariates are way more important than maybe some of the systems biology models. So with that, I'll just acknowledge that this work was done when I was still at Ohio State University, and I received funding from various different sources. So part from NSF, NIH, and MBI, but of course, I think the majority of it was the university's President's Postdoctoral Scholars Program. So with that, I'll stop here and take your question. I might have gone a couple of minutes